Hi guys, this is Muzammil Hussain Rammay, and I am a postdoc researcher at University of Stavanger, Norway. And today I am going to talk about the topic related to real-time probabilistic inversion of DNN-based DeepEM model while accounting for model error. So, so some motivation before I presenting my talk. So, uh, so the inverse modeling can be non-unique and multimodal. And if we do inversion neglecting model error, there is a possibility that we get bias input parameters. And if you observe data mismatch after inversion, there could be two reasons for that. Either we somehow trapped or stuck into a local minima, or we could have a model error in our forward model. So the challenge is extent of multimodality and model error is unknown. Uh, so how can we quantify the unknown contribution of model error and multimodality? So the idea here, it can be assessed using two variants of the iterative ensemble smoothers. One is iterative ensemble smoother for a perfect model, which is I'm using here ESMDA, but there are different other versions also available in the literature. And the other one is the flexible iterative ensemble smoother for an imperfect model. So if we have imperfect model, then this variant of the iterative ensemble smoother could be useful. So so here my inverse problem description is basically it's a dynamical system where the well is drilled into the earth, and we have some measurements, electromagnetic measurements while drilling. So it's a real-time procedure. And using these measurements, we basically try to estimate the layers, Earth's properties. Like if we have, for example, this layered Earth system, we have different layers which has different resistivities and the layer thicknesses. So using these real-time measurements, we need to estimate these properties so that we can and we can get the optimal decision for new position of the well placement. So we call it as a geosteering. So the idea here is so in the scenarios, in the present situations, usually we do have logging simulators. But the thing is, logging simulators are too expensive to do real-time inversions. So the idea here is to get the map of a logging simulator using some deep neural network. And so the in this work, I already have a trained deep neural network, DNN, which takes the Earth properties and the well trajectory as an input and produces the output as a electromagnetic signal. So here, the setup of the problem is basically the resistivity is sampled is from 1 to 122 ohm meter range, and we have thicknesses from 0.3 to 20 meters. So this is just a random minimum maximum ranges for the Earth layer system we have. So we are using two iterative ensemble smoothers for doing that. So the idea is to capture the uncertainties during real-time inversion. So the workflow is like that. So we have different realizations of the Earth model, which is basically S1, S2, S3. And we combine these realizations and provide to the deep neural network. And it gives us the different realizations of the electromagnetic measurements. Once we have electromagnetic signals and we have the real-time data, we can update our model using these two iterative ensemble smoothers, which is one is the ESMD and the second one is the flexible IES. And we do it iteratively unless we match the data. and the final one is the update time. So two procedure for that. Either we account for model error or not. So if we don't account for model error, so there is an assumption that our forward model or deep neural network is a perfect representation of the real system. And this basically ESMD takes deep neural network, well trajectory, and observed data, and the M prior, which is the Earth properties realizations, as an input, and gives us the posterior, which is the estimated results of the Earth layers properties. So we can do using flexible IES. The good thing about this algorithm, it uses the data misfit or residual to account for model error. And it could be also useful for inverting both types of perfect and imperfect models. So why the deep neural network model could be imperfect? Because once we have a trained deep neural network and we have new observations, or then there is a possibility we could have a model error in it. So we cannot expect a deep neural network as a complete perfect representation of the neural real system. So that's why we want to account for model error as well. So first test case is the inversion of DNN in the absence of multimodality. So if we estimate only layers resistivity, so our inversion problem is somehow unimodal, it's not multimodal. And so if we do inversion in the absence of multimodality, what would we get? And this test case is basically showing that. So here is the ESMDA results. This is basically y-axis showing the electromagnetic signals. Green is the prior, red is the observed data, and the blue is the posterior. So blue, basically, if our model is perfect. So here I am considering my deep neural network model as a perfect representation. So how I am considering this, I am generating the observed data from the same deep neural network. So if I did like that, the inversion, so I can get the exact match, because I am getting, so my deep neural network is acting like a perfect model. So both algorithms could give me a perfect match. Here I don't have any measurement error, so my devices are fairly, so they don't have any type of measurement error. So any type of uncertainty which would be induced, it would be related to model error. So I get the exact match from using ESMDA and flexible IES from both algorithms. So, and in terms of the input parameter estimation, so the first row representing ESMDA result, the second row is the flexible IES, and the red one is the reference truth, and the blue is the posterior, which is basically red is covering the blue, so we cannot see. But here the layers resistivity R2, R4, R6, we get the exact estimation of the R2, R4, R6. And if we have in case of imperfect model, we have a model error in it, and ESMDA provides us the reasonable match, although it's not exact as before, but it's a reasonable match. However, flexible IES gives us the different results as compared to ESMDA. So basically, this algorithm, flexible iterative ensemble, could account for model errors. So basically, it tries to capture the model error during inversion. So in case of imperfect model, we could expect different estimation results from both algorithms. And so in terms of input parameter estimation, the red, which is the reference, and the blue is the posterior, if you notice that it is biased. So the model error effect here, and I couldn't get the exact parameter as input parameter using ESMDA, the first raw. Here, a model error doesn't affect very much log R4, but the important thing, the 6-layer resistivity, it's completely off. So it's like a completely wrong estimation. So here the model error affect a lot. But however, if you notice, the flexible IES tries to capture and it provides us the more reliable estimate of the parameters. So it tries to capture the model error uncertainty. So and reduces the bias in the input parameter estimation. And for R2 and R6 for both. So test case 2 is related to basically estimation. So joint estimation of layers resistivity and thickness. So here we observe the multimodality issue. So if we have a multimodality issue, so how we deduct whether it's a multimodality issue or not. So I am taking this observation from the same deep neural network, not from the real system. So I am expecting a perfect match, but I couldn't get a perfect match using both algorithms, as we get using previous test case. But it appears that I couldn't get the match, and it appears that it's trapped to some local mode of the posterior, or trapped to the local minima, in other words. Flexible IES provides some kind of different behavior as compared to ESMDA. It basically didn't converge to a single mode of the posterior. It basically tries to evaluate different modes of the posterior, and somehow it covers the data, but not matching the data. So during real-time inversion, if we don't have enough time to basically avoid multimodality, flexible IES could be, although it's not very perfect, it's not very good as well. We have a lot of uncertainty, but it could be useful as compared to the ESMDA. We will observe. So if we see the parameter estimation results, so because it traps to the local mode, all parameters are completely off, log R1, log R3, log R6, which is very bad, yeah. And it's a severe multimodality issue. But because flexible IES basically covers different modes of the posterior, so it gives us, it tries to cover the parameter results, the reference result. Although I have very high uncertainty, but of course the reliability, one can say, it's better to get the complete wrong estimation. So these results would be better to get a completely wrong estimation results. So how can we avoid this multimodality issue? If we have a time during real-time inversion, then informed prior could be useful to avoid the multimodality issue. How can we get informed prior? So it basically varies from system through system. Here we are getting an informed prior using some trial and error approach, and we reduce the thickness search space so that, and by using informed prior, we somehow avoid the multimodality issue and we get the exact match using both algorithms. So, and our estimations are also exact using both algorithms. And thicknesses estimation are also exact. But here the model is perfect. So I am basically getting the observation from the same deep neural network. What if I have an imperfect model? That is like, what if I have getting the observation from real system? Then we can have a model error as well. So if we have a model error, ESMDA can give us, not very good match, like, match, we can say, not very good, but due to the model error thing. But flexible IES tries to capture the data and basically tries to account for the model error. So here, basically, we avoid the multimodality issue. Now the issue is the model error, because we are using the same informed prior, which we use to avoid multimodality issue. So in terms of parameter estimation, so the first raw ESMDA results, because it doesn't account for model error, so we get the wrong estimation of the parameters. Like log R6 is very completely off, log R2, log R. They are also not exactly equal to truth. But flexible IS tries to reduce the model bias, and log R to log R4, it basically more close to the truth. And of course, it also tried to reduce the bias in the very wrong estimation of log R. So now we have more reliable estimation as well. And in terms of thicknesses as well, the good thing is if ESMDA performs better for certain parameters, B1, B3, so we have, so the model error doesn't affect too much. So the flexible IS also doesn't affect here too much. So we have almost have the similar type of estimation using both algorithms. But here, if the model error contributes a lot, like the thickness of the layers 5, the estimation of the thickness is completely wrong. So, but here, my flexible IS tries to capture the truth thickness because it accounts for the model error. So the conclusions are iterative ensemble smoothers could provide an exact estimate when there are no model errors, measurement error, multimodality, and non-uniqueness. ESMDA could be useful to account for measurement errors, but not the model errors. Flexible iterative ensemble smoother is useful to reduce the bias during inversion of imperfect models. It is useful to quantify the unknown model error uncertainty, and it's useful to obtain more reliable model or input parameters. Multimodality could be identified using the inversion of perfect model, like if we generate the observation from the same model. So we could identify multimodality issue. Because in perfect model, we don't have model error. If we have a data mismatch from perfect model, it means there is a multimodality issue. So local modes, local minima could be avoided by using the informed prior. So if our prior is informed, we could avoid local modes or local minima. Combined analysis of ESMD and flexible IES could be useful to ensure the reliability of the estimation. So if in reality, we don't know the exact truth. So if we combine the analysis of ESMD and flexible IES, and it gives us the same results. We observed that if the parameter results are exactly same, then both algorithms almost give the same results. So the combined analysis of both algorithms could be useful to ensure the reliability of the estimation. So thank you. These are the references. So one is ESMDA, flexible IES, and the already trained deep neural network, which is used in this study. Thank you.